Okay, suspension bridges are a very specific type of quadratic application problem. The Golden Gate Bridge is an example, the Hakata Bridge is another example. I mean, there are other bridges that still have parabolic support to them, but the suspension bridges are something different from even those. And what they consist of is they consist of two vertical upright towers, a driving lane, and that driving lane is usually assigned ground level because usually these are built over canyons, waterways, things like that. So this would be considered ground level, and the vertical towers extend a little bit underneath the roadway as well as quite a ways up above the roadway. You've got diagonal support cables here. It's actually several hundreds of cables all wound together to make them thick and very supportive. And then finally you have the actual suspension arch, and of course that's the actual parabola. This definition right here, the main span, is the single biggest place where people make mistakes on these problems, because on the test when you're given information about the main span of a bridge, some people mix it up as the whole length of the bridge, even though it sounds kind of self-defining. It is the span of the main section of the bridge. By definition, it is the span between the two vertical upright towers. So make sure you've got that definition correct. Now the different parts of the bridge are going to be different types of equations. The two vertical support towers are each going to have the equations of vertical lines.
Banana!
The driving lane is going to be a horizontal line. The two diagonal support cables are what we call oblique lines, and oblique means angled. And then the actual suspension arch is the parabola. So what's going to happen is you're going to be given a situation where you're given enough information to assign coordinates to various locations along the picture of the bridge. So here's a picture of the Hakata Bridge. Remember that the driving lane, so this section right here, is at ground level, so it's automatically assigned a y value of 0. That's essentially your x-axis. So all of those points along there have a y coordinate of 0. You could go from right to left, but then all of your x coordinates would be negative. So normally when you're looking at the picture of it, you assign the left edge of it an x coordinate of 0. And then from there you read the description of the bridge to finish filling in the remainder of the information. So it says the main span of the bridge is 560 meters. That doesn't help us quite yet. We're going to get there. So this is 560 meters between the two vertical upright towers. The vertical towers are 60 meters tall from the driving lane to the top. So that means from right here to right here. That's 60. Okay? And so that means that if this point is at a height of 0, we do now know that both of the vertical support towers reach a y value of 60 up at the top, which those 2 points are up at the top. And then finally it says the diagonal supports are 100 meters long from the driving lane to the top. So this is the diagonal support. It's 100 meters long from where it touches the driving lane to where it touches the top. So that's 100. And we need that information because we need to find this distance right here. And the triangle created by the diagonal cable, the driving lane, and the vertical tower is a right triangle. Not only that, it's a 3, 4, 5 right triangle that's simply had a scale factor applied to it. So this side is the side that was 3, and it got multiplied by 20. That side was the side that was 5, and it got multiplied by 20. So that makes this side 80. Or you can use the Pythagorean theorem. Obviously, some of the numbers might get pretty big if you try to do that, though. So actually, we now actually have enough information to label all of the other points along our bridge. So we start over here at 0, 0. We go 80 meters in this direction. And so that means that this point up here has an x-coordinate of 80. Okay, then we need to find this x-coordinate as we work our way across the bridge. We've got two ways of going about doing it, but right now, as we're going from left to right, typically what people do is they figure out, well, half of the main span would be 280. On top of the 80 you had already traveled horizontally. So that means the x-coordinate is 360. We keep working our way across, so now we're all the way 560 across the main span plus the 80 to the left of the main span. So now we're at an x-coordinate of 640, right there. And last but not least, we go another 80 to the final end of the bridge because they are symmetric. And so that would put us at 720. There's a comma there. So we now know all of the points along that bridge, and that means that we can write all of the equations. Now when the kids were in class, I had them do the backside of this as their warm-up, and then we simply checked it and answered questions on it. So you can pause it right now if you want to give it a shot for yourself, or you can keep going. Okay, and just let the video play. So it says, what is the slope of the line representing the driving lane? Remember, the driving lane is the horizontal line. Horizontal lines have a slope of 0. And the equation of a horizontal line is just y equals whatever the y value happens to be. This one happens to be y equals 0. The slope of the line representing the vertical support towers, there's lots of ways of saying it. You could say undefined or no slope. They're vertical lines. And then the equations for those vertical lines, remember you write equations for vertical lines as x equals something. And so you can list them in either order. X equals 80 was the left vertical support tower, and x equals 640 was the right vertical support tower. The left diagonal support, if you remember the visual of it, I don't really want to have to keep flipping back and forth, but we knew that this was 80 and this was 60, and we knew it hit 0, 0. So writing its equation is very easy. We know the y-intercept is 0, and we've already got the triangle drawn to do the rise over the run. And when we reduce it down, 60 over 80 reduces down to 3 over 4. And then the right diagonal support is symmetric to it, so it's still running 80, but it's dropping 60. And then we know two of the points through it. It doesn't matter which one you use, and you don't have to write slope-intercept form, but if you use the 720, 0, it is easier, because then when you start out in point-slope form, oops, eraser right there. So when you start out in point-slope form, and you use this y-coordinate right here, you just have y minus 0, so that part of the equation disappears. The slope is negative 3/4. And so you could just leave your equation y equals negative 3/4 x minus 720. If you wanted to, that'd be perfectly fine. Or if you wanted to, you could go ahead and distribute and convert it into slope-intercept form, and you would have y equals negative 3/4 x plus 540. Either one of them would be fine. But that's all stuff that we already know how to do. Those are all linear equations. This particular unit, the majority of the back side of these was writing the quadratic, which you guys have done the investigation on writing quadratic equations from a graph and from a verbal description. The only thing that's different here is that the numbers are going to get large enough that you're going to want a calculator. Okay, so I don't have a ton of room. I guess I'm going to do this over here, and if I need to, I can always erase. Remember our parabola, we knew 3 points on our parabola, our suspension arch. We knew the vertex was the point 360, 0. We knew the point 80, 60, where it touched the diagonal support cable at the top of the first vertical support tower. And then 640, I kind of ran out of room, 60. Okay, so that's a parabola that's concave up, which means that the vertex represents a minimum. And that's our vertex, that's the other name for the maximum or minimum of a parabola. There's only one root for our bridge, and it's the vertex. It's the point 360, 0. That's the only place that touches the driving lane. And of course the three synonyms for roots are the same things that they always have been: x-intercepts, solutions, and zeros. And so now we go through the process of actually writing the equation. Probably won't have room to do it all, so I can always erase, or I can bounce it to an empty slide. But remember that we've only got one intercept, so we can't use typical intercept form. Vertex form is actually going to be a type of intercept form in this case, because our vertex is our intercept. So I'm going to start out my vertex form, y equals a, and I plug in my vertex first, so x minus 360 squared. And then I don't need to put the plus 0 right there. So I'm actually going to erase it. Just remember that that's where the y-coordinate for the vertex would go. Ours just happens to be at 0. And then the second step of the process is to plug in one of the other points on the arch to solve for a. And it doesn't matter which one you do. I will tell you that you're less accident prone with this one. And you'll see why in just a sec. If I plug in the 60 here, plug in the 640 there. Okay, so here's the reason that it's less accident prone. When you do this subtraction step right here, you're not going to get a negative number. And that way when you square it, you won't have to worry about a sign change. It sounds pretty easy, but if people plug this point in and then subtract, they're going to get a negative. And then if they're relying on their calculator to do the squaring, sometimes they don't catch that it's not supposed to be negative anymore. Okay, so what we have is we have 60 is equal to a times, and that's why the calculator comes in handy. 78,400. You can see it's going to be an obnoxious, horrible fraction. So a ends up being equal to 60 over 78400, which you, once again, want to rely on your calculator to reduce that for you. And that reduces, sorry, obviously the dogs went crazy. So that reduces down to 3 over 3920. So my vertex form is done. It is y equals 3 over 3920 x minus 360 squared. Okay, I'm going to go ahead and erase the sketch of my, so that I can put the squared in there. Okay, there's my squared. And then converting it to standard form, remember from the intro notes, all we have to do is follow our order of operations. But because we don't have a number back here at the end, we don't have to worry about the final step. We won't have any like terms to combine. So all we have to do is the foiling and the distributing after that. And once again, we're going to rely heavily on our calculator for those numbers. So there's my a value. When I do my foiling, I get x squared minus 720x plus 129,600. And then I distribute through, and I get y equals 3 over 3920x squared minus. Now keep in mind that all of the numbers in this entire equation, A, B, or almost B, on the inside terms, and C on the inside terms, what I end up with are numbers that are all somehow related to the product or the reduced numbers that generated right here when I did 280 squared. So what that means is that when you distribute and you multiply in your calculator, you're going to end up with prettier reduced fractions or no fraction at all. So for example, when I distribute here to the 720x and I type it in my calculator and I convert it, it simply becomes 27 over 49x. Still a relatively messy fraction, but it's far prettier than the others. And then when I take that fraction, a value, and I multiply it by the 129,600, I end up with a number large enough. I could write it as a mixed number. I don't have a preference. You guys know I like improper fractions. I don't mind improper fractions, so you can leave it like that, or you can convert it to a mixed number, and your calculator will even do that for you. You still have to know what you're doing with your calculator to make it work. Okay, so sorry the notes are a little late coming, but hopefully this helps you guys understand the suspension bridges. Just keep in mind that if you have a bridge with a different kind of parabolic arch to it, the equations are going to work out differently, but the process is the same. Use the word problem to assign coordinates wherever you can, and then you can write the equation. If you have any questions, you can ask me in class tomorrow. Remember, the test has been pushed back a day.